like right before. All right, we're going to go ahead and get started. Welcome to our Math 106 review session for exam 3. This exam is going to cover voting and apportionment. So we've got several prepared problems, and those have been dropped in the chat. So you can look at these along with us as we go through. Also take questions at any time. So please feel free to drop a question in the chat or to speak up at any point along the way, or at any point when we stop, if there's another one that you'd like to see. All right, so looking at our first question on this review, this is just looking at preference ballots, and we're going to make a preference schedule of these ballots. So we can see on this one, it says the board of directors of a National Mathematics Association are considering 3 cities, Chicago, Philadelphia, and Miami, in which to hold their next annual conference. And we can see all their preference ballots for all the people that voted on this. So to make our preference schedule, we can really start with any one of these. I'm just going to start with the first one. So that first one, they voted PMC, which means that their first preference is Philadelphia, their second preference is Miami, third preference is Chicago. And then I'm going to see how many ballots look like that one. So I can see that there's 1, 2, 3, 4, 5, 6, 7, 8, 9 ballots that look that same way. So I'm going to write a 9 there for the total number of voters. And then I'm going to pick another ballot. So it doesn't matter, again, which one we do next. I'm just going to do Chicago, Philadelphia, Miami. And we can see how many ballots look like that one. It's like 1, 2, 3, 4. And then we don't really know when we start how many we're going to have, but it looks like we have just 3 different types of ballots here. So the next one will be Miami, Philadelphia, Chicago. And there's 1, 2, 3, 4, 5. And I'm just going to double check that I crossed everything out so I didn't miss any. So that would be my complete preference schedule. The next question asks how many members of the board of directors voted. So one thing I could do is I could just add up, like just count my ballots. So how many did I cross out, or how many do I have here? You can also just add up the numbers that we had at the top of our preference schedule. So we had 9 ballots that had PMC, 4 with CPM, 5 with MPC. So that would be a total of 18 voters. Same thing if we count our ballots. And then part C asks us to just recreate our preference schedule using percentages. So it's going to look the same. It's just instead of a number of voters, I'm going to put a percent in. So I know that the 18 voters total, 9 of them voted Philadelphia, Miami, Chicago in that order. So I would do 9 divided by 18. And then you can change that to a percent by moving the decimal 2 spaces or multiplying by 100. So in this case, that's 50%. Then I can see on the next one, CPM, that's 4 out of 18. So depending on what we're asked to round to, I'm just going to round it to the nearest 1/10 of a percent. So 22.2%. And then the last one here is 5 out of 18 voters. So if I round that, that's going to end up rounding to 27.8%. And every time you do this, this should add up to 100% or close to it. It might be a little bit off just based on rounding error. I'll stop here. Any questions I can take at this point? All right, so part D asks, how many votes would I need for a majority? So in order to understand this, we need to know what a majority means. So this is something that you could look at your reference sheet for some guidance. So we have our voting reference sheet. It says majority method, the candidate that gets more than 50% of the votes is the winner. So in order to have a majority, you would have to have more than 50% or more than half. So what I would do is I would just say, okay, how many voters did we have? We had 18 voters. So if I take 18 and divide that by 2, divide that in half, that would be 9 voters. So 9 voters would be half, but since majority means more than half, I would need to go up to the next whole number. So in this case, we would actually need 10 votes for a majority. So then it wants us to determine the winner of the election using the plurality method. So again, you can look at your reference sheet for this. It says on there, the first one on the top says plurality method, the candidate with the most first place votes is the winner. So I would just count just first place votes. So I can see that if I just look at first place votes, Philadelphia had 9. And Chicago had 4 votes. Miami had 5. So I can see who has the most votes. In this case, it would be Philadelphia. All right, and then the last question it asks here is, did the plurality winner have a majority? A lot of times people think that they automatically do, but if you have more than 2 candidates, they don't necessarily. In this case, Philadelphia only had 9 votes, and we said that in order to have more than half, you would actually need 10 votes. So in this case, the plurality winner did not have a majority. They were 1 vote away. Any questions, anything I can go over from this problem or other questions relating to this? All right, so then we're going to get into the different voting methods. This one is the approval voting. So in this case, it says there's 4 patients, A, B, C, and D, in need of an elective surgery who have applied for a special program that offers free surgeries to those with a financial need. So there are 29 surgeons who regularly volunteer for the program, and each has marked with an X the patients for which they approve of their application. So this is a different type of ballot than your preference ballot because they're just putting X's next to any of them that they're okay with. So the program selects 1 patient per week to receive a free surgery based on the winner under approval voting. And we want to know which patient will receive the surgery. So what I would do for this is I would just tally this up for each, in this case, each patient. So starting with patient A, I can see that 4 voters approved of A here. These 5 voters also approved of A, and these 5 also approved of A. So if I just add that up, I can see that A got 14 approval votes. And then I move on to the next candidate. So the next candidate, if I do B next, I can see that B got 5 plus 6 plus 4. So it looks like 15 approval votes for B. C got 5 plus 4 plus 5, or 14 for C. And then D got 4 plus 6 plus 4. So again, 14 for D. So it was close, but in this case, I can see that B had the most number of votes. So B would end up being the one that was chosen. Questions I can answer on approval vote? Okay, this next example is getting a group of friends to poll their favorite flavors for ice cream. The choices here are chocolate, vanilla, strawberry, pistachio. So we're going to use the same example to do several different voting methods. So this is asking us to determine the winner using the board account method, the plurality with elimination method, and the pairwise comparison method. So these are the other 3 methods that you'll need to know. So you do have brief descriptions of these. So if you look at your voting reference here, let's just start with the first one, part A. They ask for a board account. So if you look at this, it says it requires the voter rank each candidate from their most favorable to least favorable. It assigns 1 point to the last place candidate, 2 points to the next to last place candidate, and so on. So the candidate then with the most points among all the voters wins the election. So we'll go through that one first. So in this case, since there's 4 choices between the 4 different flavors of ice cream, that means that we've got our voters to rank them first, second, third, and fourth most preferred. So anyone that got ranked 4th is only going to get 1 point. Anyone that gets ranked 3rd is worth 2 points. Each one that's ranked 2nd is worth 3 points. And then any that were ranked 1st is worth 4 points. So you just start with 1 point and go up from there. So then I would do this candidate by candidate. I'm just going to start with chocolate because that's my favorite. So chocolate, if I look at what they got here, I can see that the first 6 voters in the first column, they ranked chocolate as their second favorite. So that means that they're giving chocolate 3 points, right? But that's 3 points from each of the 6 voters. I would do 6 times 3 points each. And then if I look at the next column, those 8 voters ranked chocolate last. So I would say those 8 voters gave chocolate only 1 point, but we're doing that 8 times. Since there's 8 voters there. The next column, I have 5 voters give chocolate 4 points. And in the last column, there were 2 voters that gave chocolate 3 points. So all I'm going to do here is just multiply all those together and then add all that up. So in this case, I will get that chocolate has, let's see, 18 plus 8 plus 20 plus 6. So they're getting 52 points. And then I'm going to do this for the next candidate. So I'll just move on to vanilla. So vanilla got 2 points from the 6 voters in the first column. They got 3 points from the 8 voters in the second column. They also got 3 points from the 5 voters in the third column, and then they got 4 points from the 2 voters in the last column. You'll notice the way that I'm writing this, I'm being very intentional here, and I'm making sure that I line things up and write them in the same order each time. And you'll see when I'm done, that makes it a little bit easier to check. So if I add all this up, this is going to be 12 plus 24 plus 15 plus 8. So I'm getting 59 points for vanilla. And let's just do strawberry next. So for strawberry is getting only 1 point from the first 6 voters. They're getting 4 points from the next 8 voters. 2 points from the next 5 voters. And 2 points from the last 2 voters. This is going to be 6 plus 32 plus 10 plus 4. So 52 points as well, strawberry. And then last, let's do pistachio. So the first 6 voters like pistachio the best. They're giving pistachio 4 points. The next 8 voters give pistachio 2 points. The next 5 give only 1 point. And then the last 2 give only 1 point. So this is going to be 24 plus 16 plus 5 plus 2, 47 points for pistachio. And then real quick before I find my winner, I'm just going to check and see. And what I can see here is that what should happen is this column all of these columns should all have the same first number. So this is just a quick way to check that I've done this correctly. And then I should also see that in every column, because I lined this up this way, in every column, there should be a 1, a 2, a 3, and a 4. So I'm just gonna just check that real quick. And that's just a quick way to make sure that I didn't make a small error just when I was recording. The fact that I have a 1, 2, 3, and 4 in each column. And since that all looks good, I'm just gonna say whoever has the most points wins. In this case, that's sad, it's vanilla. Questions on this method, word account method? All right, so we're going to do the same problem again. We're going to do this with a different method this time. So the next one they asked for here is the plurality with elimination method. So I think what can often be difficult about these is just remembering which method is what, but you don't have to do that, right? So you've got a reference sheet that can kind of jog your memory and say, which one was this again? So let me read that description real quick from the reference sheet. So this is plurality with elimination. This is sometimes called IRV, or instant runoff voting. It says if no candidate has a majority of first place votes, then the candidate with the least number of first place votes is eliminated. And then the remaining candidates move up on the ballots. And so that's going to change the number of first place votes. So then we recount that. And then this process continues until a candidate gets a majority of first place votes, and then that one is declared winner. So runoff voting is really tedious if you do it in real life, if you don't have a preference ballot, because you have to keep going back and asking people to re-vote. But since we have a preference ballot, we don't have to do that. This is going to be fairly quick and painless, we hope. So I would call this round 1. And for round 1, all I'm going to do is just look at the first place votes, right? I'm just looking at that first row, and I'm going to tally up the votes for each candidate. So in this case, my candidates are chocolate, vanilla, strawberry, and pistachio. And I can see that chocolate has 5 votes, vanilla has 2, strawberry has 8, and pistachio has 6 first place votes. And so if a candidate has a majority, then right now we're done. We don't have to go to round 2. We would just say whoever won the majority wins this election. So how do I know if they have a majority? I'm going to do the same thing we did on that first problem. So if I add up all my voters here, I've got 6 plus 8 plus 5 plus 2. So I can see that there's a total of 21 voters, 21 friends voting on their favorite ice cream flavor. And so half of that, if I do 21 divided by 2, that's going to give me 10.5, right? So 10.5 is half of 21. A majority, though, is more than half. So I have to go up to the next whole number. So that means that I would actually need 11 votes if I wanted to get a majority. So if someone has 11 votes right now, I'm finished. Unfortunately, none of the flavors do. So this means I'm going to have to go to round 2. So for round 2, I'm going to eliminate whoever had the fewest number of votes. In this case, that's vanilla. So vanilla had the fewest number of first place votes, so they are eliminated. And so when I go to round 2, I'm only going to total up the votes for chocolate, strawberry, and pistachio. And I'm going to go ahead when I do this, and I'm actually also going to just cross them out. And this is good to do if you can erase and erase it later. So I'm just going to go ahead and cross out all the B's in my table. So my totals are going to be different, right? This is going to be different this time because vanilla's votes, so they had 2 votes, but now those voters would vote for their second place choice. So if I look at how many votes chocolate has, so I've still got these 5 voters that are voting for chocolate, but now those 2 voters that would have voted vanilla are going to vote for their second place choice, which was chocolate. So that means chocolate now has 7 votes, right? The other ones in this case didn't change. Strawberry still has 8 votes. Pistachio still has 6 first place votes. All right, so does anyone have a majority? No, so nobody has the 11 votes that we need for a majority, which means I'm gonna have to go to round 3. So for round 3, I'm gonna eliminate whoever has the fewest number of votes. That's pistachio in this case. So now it is just down to chocolate versus strawberry. So when I look at this for chocolate versus strawberry, one way you can do it is you could cross out all the P's and just look at what's left. Another way you can do that if you don't want to cross things out is you could just look at how many columns have chocolate higher than strawberry and how many have strawberry higher than chocolate. So like I can see on the first column, those 6 voters, they listed chocolate higher on the list than they listed strawberry. So those would be votes for chocolate. The second column, the 8 voters, they had strawberry listed first. So they're going to vote for strawberry. The 5 voters had chocolate listed first. So they're going to vote for chocolate. The last 2 voters, chocolate was listed higher than strawberry. So they're also going to vote for chocolate. So I can see that the 6, the 5, and the 2 voters are all going to vote for chocolate over strawberry because chocolate is listed higher in the column than strawberry is. So let's see, 6 plus 5 plus 2, 13. And then strawberry only has the 8 votes. So does someone have a majority? By the time you get it down to 2, someone always should, unless it's a tie. So in this case, yes, chocolate has 13, which is more than the 11 needed. So all is right with the world, chocolate wins. Any questions on this method? So this is pretty typical that we'll see possibly different winners depending on the method that we choose. We're going to do our last method, which is pairwise comparison. So I'm going to go to my reference sheet and just kind of remind myself what that means. This is sometimes called Copeland's method. In pairwise comparison method, we match each candidate head to head against every other candidate. So the winner of each pairwise comparison gets a point, the loser 0 points. If there is a tie between 2 candidates, we give them each half a point. After all the pairwise comparisons are made, the candidate with the most points wins. So we're going to have to do comparisons between each pair of candidates. Luckily for us, this only has 4 candidates, so that shouldn't be too many, but this could get pretty tedious if we had more. So I have one pairwise comparison that I might start with, might be, say, chocolate, vanilla. That would be one comparison. But I could also do chocolate versus strawberry. I could also do chocolate versus pistachio. And I kind of like to be systematic here. So you'll notice I paired chocolate up against every other candidate. So then I might move on to vanilla. So vanilla against every other candidate. Well, I've already done vanilla versus chocolate, so I don't want to do that again. I want to be careful not to do that one twice. So I've already done vanilla versus chocolate, but I could do vanilla versus strawberry and vanilla versus pistachio. And then let me see, I need strawberry against everybody. I've already done strawberry versus chocolate and strawberry versus vanilla, but I still need strawberry versus pistachio. And by the time I get to that last one, I should already have them all. By the time I do pistachio versus everybody, I've already got pistachio up against every other flavor. So in this case, I've got 6 pairwise comparisons that I'm going to do. All right, so let's go through these. So let's start with chocolate versus vanilla. So all I'm doing here is looking at my original preference schedule, and I'm looking for where is chocolate listed higher than vanilla. These 6 voters listed chocolate higher than vanilla. These 5 voters listed chocolate higher than vanilla. But these 8 and these 2 actually listed vanilla higher than chocolate. So if it came down to just those two candidates, I can see that 11 voters would vote for chocolate and 10 voters would vote for vanilla. This is going to be a vote of 11 to 10, a very close one. But ultimately, chocolate beat out vanilla by 1 vote. So that means that chocolate is going to get the point on that one. And this is how I would typically show my work for this. So then I'm going to go to the next one. So chocolate versus strawberry. So looking at that, which columns have chocolate listed higher than strawberry? I can see that these 6 voters like chocolate better than they like strawberry because it's listed higher. These 5 voters and these 2 voters, those all prefer chocolate more than they prefer strawberry. So that's 6 plus 5 plus 2. And then that only leaves 8 voters in that leftover column for strawberry. So again, that's a point for chocolate. So then the next one was chocolate versus pistachio. And I can see that these 2 columns listed chocolate higher than pistachio. The other 2 columns listed pistachio higher than chocolate. So for chocolate versus pistachio, this would actually be 7 to 14. So actually pistachio gets that point. Next, we're going to do vanilla versus strawberry. How many voters prefer vanilla more than they prefer strawberry? We're getting, looks like 13 that prefer vanilla and only 8 that prefer strawberry better than they prefer vanilla. So that's a point for vanilla. Vanilla versus pistachio. So these 8 plus these 5 plus these 2 all prefer vanilla more than pistachio. So that's what, 15 to 6. That's a point for vanilla as well. And then last is strawberry versus pistachio. So I can see that these 8 voters plus these 5 plus these 2 all prefer strawberry more than they prefer pistachio. So only the 6 votes for pistachio. So that's also 15 to 6. So that's a vote for strawberry. So now all I'm going to do is just tally up my points. So I can see that from this, chocolate got 2 points. Vanilla got 2 points. Pistachio got 1 point and strawberry got 1 point. So we actually have a tie, and I would just declare that here. So in this case, say that chocolate and vanilla tied. Can I answer any questions on any of these voting methods? All right, so the rest of the voting problems that I have prepared here are relating to like counting our pairwise comparisons and then some of the fairness criterion. So this first one says in the Gavin Newsom gubernatorial recall election in California this past fall, there were a total of 46 candidates. So if California were to have considered determining the winners through the method of pairwise comparisons, how many pairwise comparisons would have to be considered? So you do need to know this formula, but this will determine for you the number of pairwise comparisons. So if you do C minus 1 times C divided by 2, where C is the number of candidates that you have, in this case 46. So this will determine how many different pairwise comparisons you would have to do. So in the last example, we had 4 candidates. So if we did 4 times 4 minus 1, that would give us 12. Divide that by 2, and you get 6, which is exactly what we did. We did 6 pairwise comparisons. So if we had 46 candidates, going to be 45 times 46, and then divide that by 2. 45 times 46, 2070, and divide that by 2. So you can imagine we would not want to go through the work of doing that 1035 pairwise comparisons. So having to do A versus B, A versus C, A versus D, do that 1,035 times. Questions on that one? All right, so let's start looking at the fairness criterion. So you do have information about this on your reference sheet, so you can use this as you are solving these problems. So we can see that there are 4 voting criteria. So these are what we call our fairness criterion. Basically, these are things that should happen in order for a voting method to be fair, although what we see with Kenneth Arrow's theorem is that no voting method is perfect. It's been mathematically proven that a perfect voting method does not exist, and no matter what, there is always a possibility that your voting method could violate at least one of these fairness criteria. But if a method were perfectly fair, it would satisfy all of these. So just real quick, just to kind of refresh, the head-to-head comparison criterion just states that if a particular candidate wins all head-to-head comparisons, then that candidate should win the election, right? And that makes sense. That sounds fair. So if that doesn't happen, if there's someone that wins all head-to-head comparisons and they don't win the election, that would violate this criterion because that doesn't sound very fair. The majority criterion states that if a candidate receives a majority, then that candidate should be the winner. So if you do have a candidate that gets a majority and someone else wins, that would violate this. The monotonicity criterion states that if a candidate wins an election and a re-election is held in which the only changes in voting favor the original winning candidate, then that candidate should still win. And again, that sounds fair. It sounds like if we have voters change, but they only change to who was winning, that person should still be winning. And if that doesn't happen, it violates this criterion. And then the irrelevant alternatives criterion just requires that if a certain candidate wins the election and then one of the other irrelevant candidates is removed from the ballot, and then you recount the ballots, the original winner should still win. And again, if that doesn't happen, this is violated. So let's look at some examples. See if we can identify. This is essentially multiple choice. It's going to be one of those 4. All right, so part A here says using plurality with elimination, the winner would be A, but due to exit polling information, 19 people who voted BAC changed their vote to ABC, and this causes C to win. So we can see, like, here's our original table here of votes, and we had different people voting for 3 candidates, A, B, and C. And then what happened is they had that information, that preliminary information, and then they did the actual vote. And in the actual vote, 19 of the voters in this column, right? 19 of those 24 voters decided to change their vote. They decided to vote A first, then B, then C. So that's what you're seeing in the second part here, is you're seeing that 19 of them got added to that first column, which means now there's only 5 left that voted B, then A, then C. So if you look at that, what's happening here? Well, you've got some people changing their votes, right? They're changing their votes, but it said originally, it said that the winner would be A. And so all they did was change their vote so that they were already voting for who was already winning. So they changed their vote to the winning candidate, but that cost A the election because then all of a sudden that caused C to win. So this would be an example of the monotonicity criteria. The only changes in voting were changes to favor the candidate that was already winning. But when they did that, it cost that candidate the election. All right, so B says a democratic voting method for 3 or more candidates that satisfies all 4 fairness criteria is a mathematical impossibility. That is just Kenneth-Arrow's theorem. So this is just the theorem that has been proven. It's called Arrow's impossibility theorem. It just says what I talked about previously. There is no perfect voting method. All right, so part C with the votes and candidates shown here, it says Betty wins using the board account method. So you can see we've got 4 candidates, Alan, Betty, Cindy, and Dennis. And it says that they used board account and they found that Betty wins. So what's the issue here? Like we're not changing our votes. We're not doing like head-to-head comparisons, although we could maybe try that. So if I'm looking at like my criterion here, we have like majority criterion, irrelevant alternatives, head-to-head comparison. So what's going on here? I think maybe it would just be good to look at like the first place votes. So if I look at first place votes, I can see that A would get a total of 8 first place votes. B would get a total of 4 plus 2, so that would be 6 first place votes for B. And then C's not getting any, and D's not getting any first place votes. So if I just look at first place votes, it's really down to A and B. And how many total voters are there here? Like if I add my 6, 4, 2, and 2 voters, it looks like I have a total of 14 voters. So half of 14 would be 7. And if I wanted a majority, that would need to be more than that. So that means I would need 8 votes for a majority. So does any candidate have a majority? Yeah, so barely, right? So you would need 8 votes for a majority, and that's what A has, right? So A has a majority, but if you look, so Alan has a majority, but it said that when they used the board account method, that Betty won. So the fact that Alan has a majority and didn't win this election, that's a violation of the majority criteria. Any questions there? Sometimes with these, it's good to like kind of do process of elimination. So especially if you know that there's one of each, then you can kind of rule them out. Let's look at the next one. It says using the board account with the following table, it says C wins. And then it says if A drops out, B wins. So honestly, the table here, like if you want to see us go through that with board account, we can. I'm gonna wait till the noise dies down here. All right. So we could go through the board account on this one just to see what it ends up with, but I really don't even need that based on the information they're telling me here. They're saying that C wins, and then if A drops out, then B wins. So you have some candidate that wasn't winning, drops out of the race, and when they do that, then the other candidate that wasn't related at all and was winning is now not winning, right? So you had C was winning. When A drops out, it costs C the election. So this would be our irrelevant alternatives criteria. Where basically A is our irrelevant alternative. A is an irrelevant candidate because they weren't winning, yet when they dropped out, it cost C the election. And let's look at the last one here. So this one says that B is favored over A and B is favored over C using the table shown, but B is not the plurality winner. So if they were using the plurality method to determine the election, we can see that A has the most number of votes. It has 15 votes, and B has only 13 first place votes. But they're saying that if you look at B over A, so B over A, there's actually these 13 voters and also these 3 voters prefer B more than they prefer A. So if you look at B versus A, you would have 16 voters that prefer B and only 15 that prefer A. So B is preferred over A. B is also preferred over C. So if you look at every single one of these except for the 3 voters. So these 15 voters prefer B more than they prefer C because B is listed higher. These 13 voters prefer B more than they prefer C. And only these last 3 prefer C more than they prefer B. So that means that if it's down to a head-to-head comparison between B and C, B is also preferred against C. So every head-to-head comparison, B is the preferred candidate, yet they didn't win. So this would be a violation of our head-to-head comparison criteria. And we probably could have gotten there by process of elimination just because that's the one we hadn't done yet. Any questions, any of those I can revisit, talk about, or do another example of? Okay, so this is kind of the halfway point. So this test is going to be over both voting and apportionment. This is all the voting examples that I had prepared. If you have a question about any of those, I'll be glad to do more questions on voting. But if there's no questions right now, we're going to move on then to kind of the apportionment section here. So what I've done here, I just have one example that I'm going to do repeatedly. So we have several different apportionment methods, and I'm just going to use the same example for all of those. So this example says a coastal area recently hit by a hurricane is made up of 4 townships. The National Guard has 30 planes loaded with supplies, and those must be dispatched to the different townships based on the size of their population. So we've got information here on town A, B, C, and D, and we have their population in thousands. So these are our 4 towns with their 4 populations. What they're wanting to do is they're wanting to apportion these 30 planes. So if a town has a larger population, they should get more planes. If they have a smaller population, they should get fewer planes. And we're not going to send like half a plane to one and a quarter of a plane to another. So we're going to actually apportion these. So let's start with Hamilton's method. We'll go through this with each of the 5 methods that we're doing. So Hamilton's method, on all of these, the first thing we would do is find the total. So I'm going to take the population of each one of these and just add those together. So 27.5 plus 38.3 plus 46.5 plus 76.7. And in this case, I'm getting 189. So that would tell me that the total population of all 4 towns is 189. That's in thousands. And then what we would need to do, and I would show work for this, your standard divisor is going to be whatever you get when you take the total population, in this case 189, and divide it by however many seats or objects you have to apportion, in this case 30 planes. So I'm going to take 189 and divide that by 30, and that's going to give me the standard divisor here of 6.3. So regardless of the method, this part is the same. And then also finding the standard quota, that's something you're going to do with each method as well. So to find the standard quota, we're going to take each state's population, or in this case, each town's population, and we're going to divide it by that standard divisor. So for the first one, I would do 27.5 divided by 6.3. And make sure you pay attention to what you're asked to round to. Let's just round these to 4 decimals to be on the safe side. So this is going to be 4.3651. And then I'll just keep doing this for each one. 38.3 divided by that standard divisor. I get 6.0794. Kind of cramming these in, so if you can't see it, let me know. Can't read my writing. 46.5 divided by 6.3 is giving me 7.38. That would actually round to 10. And then 76.7 divided by the standard divisor, 12.1746. And this is the same for each method. So if I look ahead a little bit, I've already put all these numbers on all the previous ones. So it would just, all the ones that follow this, they're all going to have those same numbers for the first part. All right, so this is when it's different depending on the method. So Hamilton's method is a fairly easy one to carry out, but it does have lots of issues when we have run into our apportionment paradoxes. So Hamilton's method, we look at our reference sheet to kind of remind us what's going on here. Hamilton's method assigns each state its lower quota and then gives surplus seats one at a time to the states whose standard quota has the largest fractional part, or in other words, the largest decimal part. So on this one, I'm going to use the lower quota. So that would be my initial allocation. So the lower quota is just what do I get if I round it down to the next whole number. So this is going to be 4, 6, 7, and 12. I'm just taking those standard quotas and rounding them down, or essentially dropping the decimal part. And so if I add those, I get 29. So the idea is that this needs to add up to however many I have to apportion, in this case, 30 planes. If it adds to 30, I'm done, right? If it doesn't add to 30, that's when I have to use whatever method I'm using. So Hamilton's method assigns the surplus one at a time. So how many surplus do I have? I just have one in this case, right? So I've apportioned 29 planes. I've got one more since I have a total of 30. So who would get the extra plane? I look at the decimal parts, and whoever has the biggest decimal part, that's who would get the surplus. So in this case, 0.3810 is the biggest decimal portion. So they're going to get the one surplus. And if I had more surplus, then I would just give it to whoever has the second biggest decimal portion. So that means that town C is going to end up getting 8 planes, and everybody else is just getting their lower quota. So 4, 6, 8, and 12. And I'll just check real quick and make sure, yeah, sure enough, that adds up to 30 planes. So essentially, this last column is my answer. That's my final apportionment with Hamilton's method. It's 4 to town A, 6 to town B, 8 to town C, and 12 to town D. Any questions on Hamilton's method? All right, so we have Jefferson's method next. So this is the same way at first. They found the total was 189. They found the standard divisor was 6.3. They found all of the standard quotas, so the same numbers that we had. And then we just needed to see, okay, what does Jefferson's method do? So let's revisit that reference sheet. Jefferson's method uses a modified divisor by trial and error until the sum of the lower quotas equals the number of seats. So this kind of jogs our memory a little bit. We know to use the lower quotas with Jefferson's method. So that part is similar with Hamilton, is they both use the lower quota. So from here, I would go ahead and write down those lower quotas. This is 4, 6, 7, and 12. And then if I add those up, of course, just like before, that adds to 29. All right, but then Jefferson handles this differently than Hamilton. So Jefferson says, okay, that didn't add up to 30. It didn't add up correctly. I need it to add to 30, which means I need this number to be larger. I need it to be 30, because that's how many planes I have. So if I need that number to be larger, that means the way I get a larger number is to choose a smaller divisor. So the divisor that we were using was the 6.3. So I'm just going to use something smaller than that, right? So technically you can try anything smaller than that. So you can try 6, you can try 5.7, you can try 5.5, you can try 6.2. When you do this in ALEKS, I know ALEKS is very particular. They want you to increment by 5s or 0.5s. So they would have you, like, since we need to choose a smaller divisor, they would have you subtract 0.5 from that. So the next one they would have you try would be 5.8. So you're welcome to do that, but technically this can be anything you want as long as it's smaller than 6.3, which means you might choose one that's different from what I would choose or what from your neighbor would choose. Somebody want to make a suggestion? What is it?
Go with 6.
Go with 6. All right, so let's see what 6 does. So I'm going to write that down. That's my modified divisor I'm choosing. All right, so let's go through this dividing by 6 instead of 6.3. So I'm going to take each population, like for town A, 27.5, and let's divide that by 6. So that's giving me 4.5833. And so then I'm going to do this for each one. So 38.3 divided by 6. So that's giving me 6.8833. And just keep doing this for each one. And this really is a trial and error process. So you might get lucky and the first thing you try works, and you might be unlucky and it's the 10th thing you try. But as we go, we're narrowing it down. We're getting closer and closer to something that will work. And there may be more than one thing that works. All right, so I've got these numbers. So again, Jefferson uses the lower quota. So I'm going to round all these down. So this is going to be 4, 6, 7, 12, and I can already tell that's not going to work because I got the same thing, right? So I got 29. So again, I need that number to be larger. I need it to be 30. So that means I need to choose something smaller, but I'm narrowing this down because now I know it has to be smaller than 6, right? So what do you want to try? We could try 5.5, 5.8, 5.75, 5.9, 5.5. Let's try it, right? And so if you're using a table like this, we might run out of space. That's normal. You can extend it. You can go on to another sheet of paper. You can erase, you can do it. We might get lucky and we might be done after this. We might have to go further. So let's do this one. So if I do 5.5, I'm just going to take this and divide each population by 5.5. I want to say, like, through the magic of television, there it is. I did work this one out ahead, so I have those, but I will make sure that everybody's caught up with me. I just took each population and divided it by that 5.5. fix that last one. I made a mistake writing that one down. All right, so let's do the lower quotas. So if I round each of these down, 5 would just stay as 5. And this would be 6, 8, 13. And if I'm lucky and that adds to 30, I'm done. What does this add to? 32. Yeah. But that helps me narrow it down, right? So this number right now is too big, right? I need this number to be 30, which means it needs to be smaller. If I need the number to be smaller, that means the way I do that is by choosing a larger divisor. So I've at least narrowed it down at something between 5.5 and 6. And so I'm just going to keep trying. All right, so I'm just going to erase just so I have some more space to work in my table here. So I know I need to choose something bigger than 5.5, smaller than 6. I feel like 6 was closer to what we wanted because 29 was closer than the 5.5 gave us. So maybe something closer to 6. 5.75. We could just go in the middle, right? We could go closer to 6. We'll try that and let's see how that goes. So 5.75. So I did this and I got 4.7826, 6.6609, 8.0870, 13.3391. I'll be glad to pause there if anyone needs help or reminder what we're doing for each population, dividing it by that 5.75. All right, so again, we're using lower quotas. So this is going to be 4, 6, 8, 13. What is that? 31. So that is still, I need that to be smaller, right? I need it to be 30, which means I need to pick something bigger, a bigger divisor. So I need something bigger than 5.75, but still smaller than 6. 5.9. Okay, let's try 5.9. So if I do 5.9, getting 4.6610, 6.4915, 7.8814, and 13. So Jefferson's method again uses lower quotas. So this is going to give me 4, 6, 7, and then that would just stay 13. What does that give me? Woohoo. So now that we got it to add up to 30, then we're done. And this is our final apportionment. So my advice, this can take a little while. So I have 2 pieces of advice on this when you do your test. One is I would save the apportionment to last. Because you want to get everything else done, just knowing that this process of trial and error can take you a little while. So that's my first piece of advice. My second piece of advice is if you really struggle with this and you just keep doing it, and you're not finding the divisor, do not erase everything and then leave that problem blank. Whatever you have, leave it there and you have a better chance of getting some partial credit on that problem, even if you didn't find the correct divisor, because we would be able to see if you know the correct process and give you as much partial credit as we can. All right, so then let's do the same thing with Adam's method. So it's the same problem, but we might have a different apportionment on this when we do it. That's pretty normal. So with Adam's method, what's the difference? Well, you look at the description on here, the description looks almost identical. Like if you look at Jefferson's, which we just did, and Adams, they read almost exactly the same, uses a modified divisor by trial and error until the sum of the, and so this is the only difference is that Adams uses upper quotas, right? So it's still this trial and error process. It's just instead of rounding down, we're going to round up. All right, so I've got the same total, the same standard divisor, the same standard quotas. My initial allocation, though, I'm going to round up. So that means this standard quota here of 4.3651, if I round that up to use the upper quota, that would be 5. For the 6.0794, if I round that up, would be 7. The next one would be 8. And the next one would be 13. So I'm just using upper quotas instead of lower. If that adds to 30, I'm done. Yeah, it doesn't work. So since this adds to 33 and I need it to add to 30, that means that I need this to be smaller, which means I need to choose a divisor that is what? That is bigger. So let's choose a larger divisor. So we could try 6.5, we could try 6.2, 6.8, 7, 6.75. Recommendation there. 6.5. I tried that one as well. I think that's a good one to try. So 6.5. So I'm going to take each of the populations and divide it by that. So 27.5 divided by 6.5. That's giving me 4.2308. 38.3 divided by 6.5. It's 5.8923. 46.5 divided by 6.5. 7.1538. And then 76.7 divided by 6.5. 11.8. All right, and then we round this up. So if I round these up, this is going to be upper quotas are 5, 6, 8, and 12. If it adds to 30, I'm done. Unfortunately, it's not. So that adds to 31, but I'm getting closer. And it still does need to be smaller. So I still need to choose a larger divisor. So I need something bigger than 6.5.
6.7.
Okay, let's try 6.7. So for 6.7, let's just divide each of these by that. I did not try this one, so I don't know if this one works or not. That's one thing about this is there's not just one correct answer. There could be more than one correct answer. So you might get a different modified divisor than what your neighbor would get and still get the same answer, the same apportionment. If you all notice that I make a mistake, let me know because I did this just now very quickly. All right, so let's see, round these up, use the upper quotas. So this would be 5, 6, 7, 12. And that does add up to 30. So when I did this ahead of time, I used a different divisor than 6.7, but I still got the same answer. I still got 5, 6, 7, 12. So there's possibly more than one correct divisor. I used 6.8 and that one also worked. So no matter what divisor you use, if you're use the method correctly, you should get 5, 6, 7, 12. Questions on Adam's method? Webster is next. So if we look at our description, again, it reads pretty much the same way, except again, the only difference is how they're rounding. So Webster's method rounds conventionally, right? So instead of always rounding down or always rounding up, we're going to round with normal rounding rules, which is, in this case, if the part behind the decimal, if that digit is 5 or higher, we'll round up. If it's 4 or lower, we'll round down. So on this first one, 4.3651, since it's a 3 behind the decimal, this will go down to 4. 6.0794, since that's a 0, we'll round down to 6. This next one, 7.3, so that would round down to 7. 12.1 would round down to 12. So these all happen to round down, but that will not always be that way. So the reason these rounded down is because the digit after the decimal was 4 or lower. All right, so let's add those up and see what we're getting. So we get 29, which is not bad, that's close. So I need that to be bigger because I'm aiming for 30. And so that means I need to choose a smaller divisor. So something smaller than 6.3, although I'm not far off, right? 29, so maybe not a whole lot smaller than 6.3. 6.1, let's try that. So we'll try 6.1. When I did that, I got 4.5082, 6.2787, 7.6230, 12.5738. I just divided each population by 6.1. That's how I got those. So you guys stop me at any point if I lost you on how I got a number. So then we're going to round these conventionally. So the fact that 4.5, the digit behind the decimal, is a 5 or higher means I'm going to round this up. So this is going to be a 5. 6.2787, since it's a 2 behind the decimal, that would round down to 6. 7.6 would round up to 8. 12.5 would round up to 13. So if this does add to 30, then I wouldn't even need the rest of my table, right? I just do this until I get to 30. In this case, yeah, 32, that's unfortunate. But now I need that number to be smaller. 6.2 sounds like a good one. So we need to choose like something that is bigger than 6.1, but smaller than 6.3. So let's just meet in the middle, right? 6.2 gives me 4.4355, 6.1774, 7.5, 12.3710. So round these conventionally. So this is going to be round down to 4, round down to 6, round up to 8, and round down to 12. And yay, that adds to 30. So that is my final apportionment. I think so far we've gotten different apportionments on all of these, and sometimes that happens, sometimes it doesn't. Sometimes you get the same answer with different methods. Any questions on any of these methods so far? All right, we've got one left, which is the Huntington Hill method, and we're doing the same example with this method. So let's look real quick at our reference sheet and see what they say about this one. All right, so Huntington Hill, this is, by the way, the one that is currently used to apportion seats in the House of Representatives to each state in the United States. So the Huntington Hill method also uses a modified divisor method with trial and error, But the assigned number of seats is determined by comparing the standard quota to the geometric mean of the lower and upper quotas. So this is a little bit more mathematical. We're going to have to find some geometric means between the lower and upper quotas. So if the state standard quota is above the geometric mean, then the standard quota is rounded up. And if the state standard quota is below the geometric mean, then the standard quota is rounded down. It's nice that that's on my reference sheet. I don't need to remember that. I'm just going to look at it and use it. So what I'm going to do here, and I've put some columns in my table for this just to make it a little easier. I'm going to go ahead and just write down all the lower quotas and all the upper quotas. So all the lower quotas, if I just round all of these down, this is going to be 4, 6, 7, 12. And then all the upper quotas would be 5, 7, 8, and 13. All right, and then I've got a column here for geometric mean. So we're going to find the geometric mean between the lower quota and the upper quota. The way that you find geometric mean between two numbers is you multiply them together and take the square root. So if I want to find the geometric mean between 4 and 5, that means I'm going to multiply those together. And then I'm going to take the square root of that. So you can do this as square root of 20, or you can even put it in your calculator as square root of 4 times 5. And so again, I'm just going to round these to 4 decimals. So on this one, I'm getting 4.4721. And then I'm just going to keep going here. So the next one, my lower quota was 6, my upper quota was 7. So I'm going to do the square root of 6 times 7, or you could just say square root of 42. One thing that's nice about the geometric mean is it will always be in between the two numbers you're finding the mean of. So if we're finding the geometric mean between 6 and 7, it's going to be 6 point something, right? And that will be the case for all of these, so you can catch any simple errors that way. So then square root of 7 times 8. I'm getting 7.4833. Then square root of 12 times 13. 12 point, this actually rounds to 4900. All right, and then based on this, I'm gonna do this process. So I'm gonna revisit that reference sheet. So it said, if the state standard quota is above the geometric mean, then it's rounded up. And if the state standard quota is below the geometric mean, it's rounded down. So I'm just going to compare my standard quota with this geometric mean. So if I compare 4.3651, that is smaller than 4.4721. So if my standard quota is smaller, I round down, or in other words, use the lower quota. So I'm going to do an initial allocation of 4. So then if I look at the next one, 6.0794 is also smaller than this geometric mean 6.4807. So that means I'm going to round down or use the lower quota, which is 6. 7.3810 is also smaller than that geometric mean of 7.4833. So I'm going to use 7. And then 12.1746 is smaller than 12.4900. So I'm going to use the lower quota of 12. So they all turned out to be smaller on this example, but that just happened to work out this way. All right, if this adds to 30, I'm finished and I don't need the rest of this. So let's see what this adds to. Almost adds to 29. So then I'm doing the same trial and error process that I've been doing. So right now I need this to be larger because I've got 30 planes to apportion to each of these towns. So I need it to be 30. And so how do I get it to be larger? I choose a smaller divisor. So something smaller than 6.3, maybe not a ton smaller. 6.2 worked before. Let's do that. Let's see how that goes. So the nice thing about this is that if I've done this previously, it should be the same numbers. So if we flip back here, we had all the numbers for 6.2, so you could just copy those down. I'll just copy them down here again, but we basically already did this on a previous problem. So we had 4.4355, 6.1774, 7.5, and 12.3710. All right, so the lower quotas here are going to be 4, 6, 7, 12. And then the upper quotas are going to be 5, 7, 8, and 13. And they won't always be the same, but in this case, they did happen to be the same as what we had on the first part of this. So that means I don't have to go through all the work. I already did it. So the geometric mean between 4 and 5 was 4.4721. Geometric mean between 6 and 7 was 6.4807. Geometric mean between 7 and 8 was 7.4833. And the geometric mean between 12 and 13 was 12.4900. And that'll often happen. You might have maybe 1 or 2 of them change, but a lot of them you can just copy them. All right, so if we compare these again, so 4.4355 is smaller than that geometric mean of 4.4721. So that means I would use the lower quota. I would use 4. Then 6.1774 is smaller than 6.4807. So I would use 6. 7.5 is bigger than 7.4833. So that means I would round up and use 8 or the upper quota. And then 12.3710 is smaller than 12.49. So I'm going to use the lower quota of 12. And I think that does it. That adds up to 30. And so this is my final apportionment is 4, 6, 8, 12. Which actually happened to be the same thing we got with Webster's, but it doesn't always work that way. It just happened to work out this time. These are the 5 apportionment methods. Any questions? Anything I can work through or talk about with those? So the last thing I have is our apportionment paradoxes and our theorems. So this is not on your reference sheet. So you do need to know these. So just to make like a quick list of all these, we have, there's the Alabama paradox. There's the population paradox. There's the new states paradox. So those are our 3 paradoxes. There's also the quota rule. And then there's also the Volinsky and Young theorem. So these are 5 things that you will not find on the reference sheet that you do need to know what they are. So the Belinsky and Young theorem, that's kind of like Arrows and possibilities theorem. It's just the theorem that says, hey, there's no perfect apportionment method, right? No matter what, any apportionment method for apportioning is going to either produce a paradox or violate the quota rule, right? There is no existence of any apportionment method that doesn't do one or the other of those things. So there's no perfect method for apportionment. They all have their flaws. The quota rule, that rule is basically the one that says that, hey, your states or your districts, they should each be assigned either their lower or their upper quota. And hopefully that makes sense. Like if we look at, the previous example, when we started, for example, like town A, their standard quota was 4.3651. That really means that based on their population, town A should have been apportioned 4.3651 planes to help in the rescue efforts, right? To help after the hurricane. But you can't assign 0.3651 of a plane, right? So we would either assign them 4 planes or 5, right? But we shouldn't see anything besides that, right? It would not be a very fair method if they got 6 planes, right? Or if they got 3 planes. So that's what the quota rule is saying. It's just saying that they should get either their lower or their upper quota. For the 3 paradoxes, so this is a lot that you have to know, but some of these kind of give away the name, right? So like quota rule kind of gives away what it is because it says it has to be the lower or upper quota, right? And it's called the quota rule. Population paradox has to do with population, right? New states paradox has to do with adding a new state, right? I think the only one that doesn't really give its name away is Alabama. And so what the Alabama paradox is, it says that if you add seats, so like in the previous example, if I added more planes, right? So if I had more planes to hand out, if that cost one of the districts a seat, then that would be the Alabama paradox, right? So adding more seats shouldn't cause anyone to lose one, right? Adding more planes shouldn't cause any of the towns to lose a plane. But if it did, that would be an example of the Alabama paradox. And I just think about seats in Alabama Stadium, if that helps. So like seats, Alabama. The population paradox has to do with population. It just says that if you have a state whose population is increasing faster than another state's population is increasing, then they should get any additional seats, not the other state. So if a state got a seat, but their population wasn't growing as fast, that would be a violation. That would be the population paradox. And then the new states paradox says, this is what happens when you add a new state, right? If you add a new state,